Okay, so now let's look at, I don't know how many of these we'll get through, but now let's try actually looking at how we can use the second derivative to really help us out sketching a graph. And there's two ways we can do this. The second derivative tells us important information relating to concavity, right? And so we can identify inflection points and intervals of positive and negative concavity, just like we do with increasing, decreasing functions for the first derivative. What you really want to do with this is you kind of want to think about each row in our table. They're all a parallel construction, right? But they impact slightly different elements, topological features, right? The first row, F or Y, whatever you want to call it, that's just talking about, where is the function above or below the x-axis, and the zeros there would be places where we have x-intercepts, right? And you've been familiar with that for many, many years. Next row in the table, the Y prime or F prime row, that's talking about increasing intervals and decreasing intervals, right? And the first derivative test allows us to locate places where we transition from negative to positive or positive to negative, and those are relative extrema, right? So that's what that one's given us: increasing, decreasing intervals, and correspondingly relative extrema. The next row we're going to populate, the second derivative row, is going to give us concave up, concave down intervals, and transitions would be inflection points. Okay, but we get bonus information. We get some bonus stuff here that's really helpful. We get this derivative test. And the second derivative test is not a test for inflection points. The second derivative test is a really efficient way to check for extrema, okay? So I'll show you what I mean. So let's look at this guy. Let's take this function and let's do everything we've done in the past, plus we'll add a new row. Okay, so first of all, we always want to start off when we're sketching a function or doing analysis on a function, we always want to start off with the domain. There's no domain imposed here. Are there any restrictions to the domain? No, it's a polynomial, right? Polynomials are super well behaved. Their domain is all real numbers. There are no omissions from the domain, right? There's nothing weird going on there. So the domain is everything. Okay, what can you tell me about symmetry on this? Because we're going to start to try to be smart about symmetry too, and cut our workload down a little bit. Give me thumbs on this. Does this thing have even symmetry? I'm seeing some people shaking their heads. It doesn't. How do you know it does not have even symmetry? And we don't have to go through the whole fancy test for symmetry, right? Even symmetry, remember, that's the one where the test for even symmetry is f of negative x equals f of x, right? That would be, if that's true, then it's got even symmetry, okay? We don't have to even go through that. And the test for odd symmetry is f of negative x equals negative f of x equals the opposite of f of x, right? We don't even have to go through all that though, because the names even and odd, where do those come from again? Do you remember? I mean, I just kind of slipped that one in at the end, but do you remember what that was from? Powers, the exponents in a polynomial, right? We work with polynomials so much that that's where we get the terms even and odd, right? If we have a polynomial with exclusively even exponents, guaranteed it's got even symmetry. If we have a polynomial with exclusively odd exponents, then we have odd symmetry. If we have a mixture, it messes it all up and we have no symmetry. So what's the outcome here? No symmetry. Yeah, there's no useful symmetry here. Okay. All right, so let's do some legwork. If we're going to analyze this function using the f prime row and the f double prime row, let's go ahead and just take some derivatives. It's a polynomial, so they're easy derivatives. So what's f prime? Okay, good. Negative 9x squared minus 18x. Looks like that's it, right? Okay, and f double prime. Negative 18x minus 18. Okay, so let's look for our critical numbers then. Where is f prime's nowhere undefined, right? Okay, but where is f prime equal to 0? We would want to maybe factor this, right? Okay, so yeah, let's go ahead and factor this. So we can take out a negative 9x, right? Okay. Times x plus 2, good. So f prime equals 0 at x equals 0 or x equals negative 2. Good. Okay. How about our second derivative? So we can look for critical numbers of the second derivative also, right? And these are different critical numbers. The critical numbers of the first derivative are, it's for what? Extrema, right? Critical numbers of the first derivative are candidates for extrema. What would critical numbers of the second derivative be candidates for? Inflection points. Agreed? So inflection points would exist in places where the second derivative is where we have critical numbers, where it's either equal to 0 or what's the one place where it could be undefined, would we say? Vertical tangents, right, okay. So I'm just going to put subscript 2 on those critical numbers so we know they're for the second derivative. Are there any second derivative critical numbers there? F double prime equals 0 when x equals 1. Yeah, negative 1. There we go, negative 1, right? Okay, so now we could go ahead and we've got our functions here. We could go ahead and make a table out of this, right? We've got our critical numbers. We know what the domain is. We know there's no symmetry. So let's go over here and let's make a table and let's discuss this. Okay. So how can we, let's go row by row, right? So here's our domain, goes from negative infinity to infinity. I guess I got my colors backwards on this. My first derivative critical numbers are yellow here. We had negative 2 and 0, right? Okay. Those were places where the first derivative was equal to 0. Okay. Negative 1 was our second derivative critical number. That's where the second derivative was equal to 0, right? Okay, so we don't even, unless we're trying to really pin this thing down and get a fairly accurate sketch where we want to know some ordered pairs, we don't even really need the Y row. Okay, that's not even really that big a deal. Okay, but how could we determine that negative 2 is a minimum and x equals 0 represents a maximum, a relative maximum? We could use the first derivative test, right? We agreed that, I mean, that's what we're going to find. We don't know that yet. I've already got everything in the chart, but let's talk about how we could do this. We could rely on the first derivative test that we've been using, and I could pick test points surrounding negative 2 and 0, right? I could use negative 1 as a first derivative test point, right? Because it's not a first derivative critical number. But if I use the first derivative test, I would still have to pick some value less than negative 2 and some value greater than 0. It works. Okay, but can anybody tell me why I don't need to do that? How could the second derivative allow me to skip those steps and just tell really quickly that -2 is a minimum and x equals 0 is a maximum. What do you think? Yeah, the concavity, right? That's the second derivative test. If the second derivative exists at a first derivative critical number, then all we have to do is find the sign of the second derivative, and that's going to, combining the fact that we have a horizontal tangent line with a positive concavity, what's the only way that could possibly happen? If we have a positive concavity and a horizontal tangent line, doesn't that mean a minimum, right? It could. Why could it not be an inflection point? Yeah, because the second derivative would have to have a value of 0 for that to be an inflection point. You get it? So there's an easy way to remember that. If you have a 0 first derivative, the horizontal tangent line, a positive second derivative means positive means it's happy. It's a happy function. It's smiling, right? So it's concave up. It's a minimum. If you have a 0 first derivative and a negative second derivative, well, that's sad function. It's concave down, so it's a maximum, right? That's the second derivative test. So what's the advantage of the second derivative test compared to the first derivative test? Do you see any practical advantage here? Because thinking about, you're going to do a bunch of these problems. Why is that one probably a little bit easier to use? What do we not have to do there that you otherwise would have to do? Test points. Yeah, you don't have to pick test points. And a lot of times, I mean, I would say a lot of times, oftentimes test points, if you have kind of a weird function, test points, it may not always be easy to evaluate the sign of the derivative at a test point. It's certainly more work, right? Okay, what's a potential disadvantage of the second derivative test? Say it again. You got to find the second derivative, right? So if you're being asked about concavity, you have to find it anyway, right? If the question is asking you about intervals of concave up and concave down, you've already done all the legwork to find the second derivative. You might as well rely on the second derivative test, right? If you're not being asked about concavity, though, then here's how I always do this, determine which test I'm going to use. If I'm not asked any specific second derivative information, then if the second derivative is a slam dunk, if it's super easy to calculate, then do it and use the second derivative test. If it's nasty, don't do it. Use the first derivative test, okay? I mean, you can see there's a lot of, when you get into analysis in math, there's a lot of kind of technique. I mean, it's just, you just want to be efficient when you're doing this stuff, right? So we can add one other piece of information. We know that we have an inflection point here. How come? With no additional work, only the work that we've already done on here to apply the second derivative test, we get another free bonus. We know that's an inflection point. How? Say it again. The second derivative is 0, and what else needs to be true for it to be an inflection point? It changes concavity, right? And so look at this. Isn't this cool? The first derivative critical numbers are acting as second derivative test points that you've already found, right? Wouldn't you agree there's only one transition in concavity, so every value to the left of 0 is going to have positive concavity. The entire function always, right? It's concave up on that entire infinite interval, and it's concave down on the interval where x is greater than 0. Isn't that cool how you can do all that stuff? So you're killing like 4 birds with one stone there, right? And you got all this free bonus information that comes out. So as a rule, and I really like these tables. I mean, that's, if you can get really good at using the tables, man, that takes you a long way in college. As a rule, you kind of want to work as far down the table as is conveniently possible to do. Because look, we get so much additional information working from the second derivative row that we didn't get working in the first derivative row. We got lots of information for very little effort in the bottom row, right? Go down as far as you conveniently can, and then use that row. Okay. Anything else? What about this? I'll just make a quick note of this. What does this mean right here? If I have a negative infinity there and an infinity there, what does that mean? Not exactly. We know it has to be a limit, right? If we're talking about an x value of negative infinity, we know we're talking about a limit because you can't get to negative infinity. So the limit, as x approaches negative infinity, the limit of the function is infinity, right? So this is end behavior stuff, isn't it? As x approaches positive infinity, the limit of the function is positive infinity. Where do we get that? Well, from, this is just, this is review, but if it's a polynomial, the leading term is the dominant term, right? The leading term is what determines the end behavior. Remember talking about that stuff? I want to dredge that up so you don't forget it, right? Remember that thing I did where remember that goofy thing where we had a big polynomial and we started off really tightly zoomed in and it looked linear, and then we backed out a little bit and it looked quadratic, and then we backed out, and eventually it was just dominated by the leading term, right? Everything else was just background noise. So the leading term is a negative odd power function, right? So what's that mean? Odd means it's doing this, and if it's negative, it's flipping over and doing that, right? So it's up on the left, down on the right, okay? Which is what our table tells us. Yes. Is that the table for that function right there? Yeah. So wouldn't the infinity on the left side, or can't they both not be infinities, or else that's a x squared? Like, wouldn't they have opposite? Oh, what the heck? That's wrong, isn't it? Yeah. Huh. Yeah, I don't know. Where's my negative? So this one should be negative, shouldn't it? Yeah. Whoops. Yeah, you're right. Should be doing that. Okay. Good point. Okay, and there's a graph of the function, right? So it's exactly what we predicted. Okay. All right. Let's try. How about one more? Is that the same one we just did? No, that's different. Yeah, that's a good one, I think. I think that's probably worth doing. Yeah. Okay. Let's zip through this one. What's the domain? All reals. Yep, all reals. Okay. Symmetry? None. Yeah. Okay, let's differentiate. Again, polynomial, so super easy, right? Just correct me. You guys know how to do this. Correct me if I make a mistake here. So what are we going to get? 3x squared plus 4x plus 5 is our first derivative. Okay. Yeah. Second derivative, 6x plus 4. Okay. Real quick, what are the zeros of the first derivative? I'm going to train you guys to be really efficient with this. This is where I'm going to apologize in advance because you're going to do a lot of these problems. But these are so important. I mean, every one you do, you just get better at these. You just feel more confident, and you see things more clearly, and you're more efficient and systematic about it. It just takes practice. Okay, there's no zeros. How do you know real quick? What do you do? What do you always check? What do you do? Yeah, but you're right. There's no magic numbers, but there still could be no magic numbers, and it could have zeros that are irrational or something, right? But it's how do we can check this? We can always look at a quadratic. Quadratics, we can do a lot of stuff really quickly. How can we just look at that and immediately ascertain? Nope, no zeros, no real zeros, which means that's what we're looking for, real zeros, right? Say it again. The discriminant, right? The part that sits under the radical in the quadratic formula determines, because that's the only square root in the quadratic formula, that's the one that tells us if we're going to have non-real zeros. If the discriminant is negative, we're getting a complex conjugate pair of imaginary zeros, right? Of non-real zeros. Agreed? And if it's, so we'll check that. We'll just check D. That's all we have to do. If we check the value of D, which is the discriminant, b squared minus 4ac, well, in this case, we're going to get 16 minus something big, right? If I do, because it's 4 times a times c, 4 times 3 times 15. I don't even need to know what that is. I just need to know it's negative, right? So I get no zeros. Okay, agreed? What if I get a positive discriminant? What's that tell me? There are how many? 2, right? In the quadratic, one for the plus and one for the minus in the quadratic formula. So I get 2 real zeros if the discriminant's positive. What if the discriminant is 0? I get 1 double 0, right? Because think about the quadratic formula. I get negative b on the top plus or minus square root of 0. Well, square root of 0 is 0. So I'm getting on the top of the quadratic formula negative b plus or minus 0. That's the same thing, negative b, right? So that would be a case where I've got a vertex on the x-axis, right? If I were graphing that quadratic. Okay, real quick, we're out of here in like 2 minutes, right? Okay, so real quick, what happens if the discriminant is a perfect square? Think about that. So the number inside the square root is a perfect square. Then it is factorable if you work hard enough, because you're going to get rational zeros. The square root's going to disappear then, right? In the quadratic formula. Does that make sense? We talked about all this stuff a couple of years ago, but it's been a while. Is that making sense? If the discriminant is a positive non-perfect square, you're guaranteed to be stuck with a square root in your answer, right? And so that's going to give you 2 irrational zeros. So that would be something that is not at all conveniently factorable, right? Does that make sense? And we'll do more and more work with, I'll show you when we get into some of these problems, we'll do more and more of that stuff, right? Okay, we'll pick this one up tomorrow. You tell me real quick, what's the definition of an inflection point? 2 parts to the definition. Switch is concavity. There's one issue. What else has to be true? Tangent line has to exist there. Okay, good. And we said also we looked at an example yesterday and we introduced the second derivative test, right? Second derivative test is a way, if we're including the second derivative row in our table, it's a way for us to really easily determine the nature of first derivative critical numbers, whether they are relative maxima, minima, or neither. Okay, and we'll look at more examples. We just need more practice with that second derivative test. There's a few important examples we need to look at, but each example will kind of give you a little more insight into how all that works. All right, one thing I definitely want to do is look at the case where a first derivative test or second derivative test fails. Like, what do you do if you get into a test and it fails, right? So we'll talk about that. Okay, and we were in the midst of this problem. We had just a polynomial. So the domain was all reals. It had neither symmetry, right? Because it had a mixture of odd and even exponents in our polynomial. And so we get no useful symmetry. We took our first derivative and we got this quadratic function, right? And this is where we left off. I asked you the question, what are the zeros? And, we were kind of talking about that, right? So one thing we always want to do, if it's not really easy to factor, if it's a really simple problem to factor, well, then no problem. Then we just find the zeros that way without giving it much thought. But if we have to advance to using like the quadratic formula or something along those lines, you always just start off with the discriminant, right? And it's work that you're going to, if the discriminant's positive, then you're just going to keep going and find the solutions with the quadratic formula. But you already did some of the work then. You already know what's going on underneath the radical. But you want to do just a quick check and see, okay, what's the nature of the discriminant? Is it positive, negative, or 0? Because that tells us something about the number of solutions. In this case, our discriminant, the stuff under the radical in the quadratic formula, was negative. So there are no solutions, right? There's no real zeros of this derivative function, and so we don't need to spend any time on it. So do we have any critical numbers? None, right? Because we know the derivative, which is a polynomial, is defined everywhere, right? It's nowhere undefined, and we just found out that it has no zeros as well, okay? So no first derivative critical numbers. What about the second derivative? Any second derivative critical numbers? Negative 2/3. Yeah, everybody agree? So for our second derivative critical numbers, we know that f second derivative, f double prime equals 0 at x equals negative 2/3, right? If we set that equal to 0 and solve. Okay, so now we can do our table, right? We know, okay, we know, I'm going to copy a couple things, not much. Okay, let's just copy this guy. I don't know if I even need to. We can just do it here. There's plenty of room. I won't even bother going to the next page. Okay, so if we make our table then, so we got x, f, f prime, and we'll add our f double prime. Okay, and our domain we said was negative infinity to infinity, and we only had one critical number. Negative 2/3 was a zero of the second derivative. Okay, no first derivative critical numbers. What else would we maybe want to add to this table? And really, that's all we need.
Would we want to do like test points to the right and left of the?
Okay, good. And we want to evaluate which row of the, which one? First derivative, second derivative. What are the test points for? Second derivative, right? Because we got a critical number there, so we need to know what could that be. If it's a zero of the second derivative, could be an inflection point, right? Does it have to be? No, it doesn't have to be, but it could be. So we would test a value, like if we just go to the left and we can just pick a number like, I don't know, just like negative 10, something like that. If I plug negative 10 in, pretty obviously, what's the sign of the second derivative? Negative. If I plug in a value like, well, 0, how about? To the right, we get positive. Okay, so then now we really know what's going on. And if we want to know, if we wanted to like actually anchor this to a specific point, we could plug negative 2/3 into the function so we could get an ordered pair, right? So we would know where the inflection point was if we wanted to be somewhat specific. If all we care about is the shape, we don't even need to do that, right? What's this thing going to look like? What's going on there? If I'm going from negative concavity to positive concavity, it's got to be going negative concavity is bowl shaped down, right? To positive concavity is bowl shaped up. But there are no horizontal tangents. So it's just going to look something like maybe, like, well, but those, okay, I messed that up, didn't I? Because there are no horizontal tangents. I just said that. So it's doing something more like, something like that. Does that make sense? Has to, right? And this is the place where the concavity is shifting. Anybody agree? Can I have any, what did I do wrong with the first one? Yeah, I had extrema in there, right? And extrema would require critical numbers of the first derivative, and there are none. Yes?
So you said 0 might be an inflection point? What if it wasn't?
Well, what if I had negative concavity there and there, right? Okay, so let's look at one like that. That's a good question. That's what I got next on the docket is one where it fails. Yep.
On this one, couldn't it have like the opposite slope, like going up?
Uh-uh.
Wait, yeah, like could it look like that?
Oh, could it be going like, I see what you're saying. Could it be going like, yeah, I could, I guess, huh? I guess it could. So how would we resolve that? Because we still could have, yeah, we still could. You're right, it could. So how could we tell?
The slope's positive.
Yeah, we'll just check the slope. Okay, what's the slope at negative 2/3? Well, it's pretty obvious it's positive, isn't it? Because the only negative term would be this one if I plug in negative 2/3. And that's not big enough to even counteract the 5, right? Even if I just took the last two terms. So if we know that you're right. I got that wrong, didn't I? The slope here should be, the slope is positive. So that's not it. It should look like, it's got to have positive slope. So it should look like this. It's concave down, we said, right? So it's going to be doing, something kind of like that, where it flips concavity, but does that make sense? Okay. This one's supposed to, you can't see it very well, but that one's supposed to be curving up. Okay. Wonder if I included a graph. Did I? Hope I did. Let's see. Oh, I did. Yep, there it is. Okay. That's it. Make sense? Okay. You really don't need much information on that chart to get a pretty accurate description, do you?